quite good. A little tip that I will give you, and this seems to be working very well actually. Having done a few zooms, this is working exactly as I planned it so far. And that's that when I've written this presentation, I've just shunted everything over to the left a bit, so that when your pictures appear down the right, it doesn't stamp all over the material. So that seems to be working well. So let's have a look. We'll have a quick look at this. Now this is just a basic picture. This is what a camera does, just to give you a flavour for certain things. And this is an old-fashioned camera, a DSLR type camera. Light comes in through the lens. A certain amount of light comes in through the lens, and the amount of light is defined by the aperture. Now telescopes have an aperture, and that's kind of built in. Camera lenses, it's adjustable, so you can change it. Telescopes, it is not generally. Then some of that light is taken through a mirror and a pentaprism, and you look through the viewfinder, and that is an optical viewfinder. So that is how they normally work. Here you have a mirror. Here behind the mirror you have a shutter. Now when you take the picture, the mirror lifts up, shutter opens for a length of time, and that is your shutter speed, and that's important as well. And another feature that sensor has behind it, that used to be a piece of film, it's not much anymore, that has a sensitivity called ISO. So you've got really three things there that go to make a picture. It's an amount of light for a length of time and onto a plate of certain sensitivity. And one of the critical things we'll talk about a bit more later is that all you need to do to make that work is get those three things right and make sure that your image is in focus. And that's all critical stuff. So that's a very basic view of what photography is. Now let's go into things a bit more. There's different sorts of cameras you can get. A lot of people carry compact cameras, and in this day and age, really, that's mostly a phone. And you'd be surprised how useful they can be for astrophotography, provided you've got a telescope. And if you've just set up your telescope to look through things in the eyepiece, you can take your compact camera or phone and actually get quite good images of bright things like the moon and planets just by holding your camera to that eyepiece. And then the more elaborate version of that is you can get little attachments that kind of holds it properly there. Now, and they're quite common now. You can, especially for phones. Phones has become, the big revolution in photography these days, and because everyone's got one, and just by sheer weight of numbers, the development has gone into them to make them really quite good. Better than they really have any right to be when you look at how tiny they are. But they do work well. Then another sort of camera is bridge camera, and a bridge camera really is sort of a compact camera with a big lens on it. And they can be quite good at taking photos of the moon and stuff, because the moon is bright. You have to remember this, that the moon is the same distance from the sun as the Earth. So the sort of photographic exposure you'd use for the moon is actually about the same as taking pictures during daytime on the Earth. It's a little darker because it's not quite as reflective, but it is very well lit by the sun. Small sensors in bridge cameras means they're not very good in low light though. So you want a digital SLR. Same basic design as the 1935 SLR reflex camera, whatever, but with digital sensors in. And they tend to be quite big sensors, what we call APS-C or full frame, which is even bigger. And they give you full control of everything. And they have generally optical viewfinders, though some also have live view systems built in now. And the next sort, really the most modern kind of camera, is the mirrorless. That's what I use. I do have DSLRs of the Sony Minolta variety, and I stopped carrying around great big cameras and great big lenses, and I bought myself a nice little mirrorless, and I fell in love with it, and I've been using them ever since. I use Panasonics. And what happens there is everything that you see is off the sensor. There is no optical viewfinder, there is no mirror. You're just seeing a picture that's Your lens projects onto the sensor and that's it. You've got a little television screen, or two actually, one on the back, one in the top, that shows you what's going on there. And that means there's all sorts of possibilities that gives rise to that's very helpful. And that means you can magnify that image, which really helps get your focus right. And they have other focusing aids like peaking. If you go, it sort of puts a shiny edge around things that are in focus. And if you're looking at things in the dark, it can turn up the gain so you can see in the dark to some extent. It starts to get noisy, but it's better than not being able to see at all. So that's really sorts of cameras. Now, the first thing you're going to need, I'll tell you now that you will not be doing astrophotography with a handheld camera. It doesn't work. So the very least you need is a tripod. Put it on a nice, sturdy, heavy tripod. And that will keep the camera still. You can just about take a picture of the moon handheld, but that's it. You also want to make sure that when you're taking your pictures that your camera stays still on the tripod. So 3 ways you can do that. Cable release is the old-fashioned way. These days you can Wi-Fi control it from your phone or tablet. Or the simple solution I very often find myself using is I just set the self-timer for 2 seconds and then you press the button, stand back, and it should have stopped shaking by then. And you get clean exposures. But then there becomes another problem. And this might surprise you a little bit until we think it through, that after a certain amount of time, which is actually not very long, the Earth's rotation starts to become an issue. And that means that if you point a camera, say, just anywhere in the sky and expose it for a minute, by the end of that minute, everything's moved. Unless you happen to be photographing the pole star, in which case that stays pretty much where it is. And so what you have to do there is you have your equatorial mount here, and this is kind of a glorified tripod, except it has an axis that points up to the North Celestial Pole, which is almost where the star Polaris is. Not quite exactly, but for a lot of purposes, as long as you're only using wide-angle lenses and stuff, you can do that. And there is a rule here. That rule, here it is down here, it's called 600 over f, which means you take the number 600 and divide it by the focal length of your lens. So let's say you've got a good old-fashioned 50mm lens that used to come with every camera a long time ago. With a full-frame sensor, you can expose that 600 over f, 600 over 50 is 12 seconds, and you'll be okay. Try and stretch that out to 30 and everything will move a bit. So that's really then when you use smaller sensors, you use a different number. So my Micro Four Thirds camera, I use 300, so I get only 6 seconds with a 50mm lens because it's magnifying more. I generally advocate that you shoot everything in manual. There is nothing that your automatic modes in your camera will do right for astrophotography. They try and average everything out to a sort of a grey thing. So if you take, for example, the moon on automatic, the moon itself will come out really bright because it's seeing the black all around it and trying to average that out. No, it doesn't work. And also shoot RAW. If you have the option to shoot RAW as well as JPEG files, I would say shoot RAW for the reason that you can do a lot more with them afterwards, including sorting out any mistakes you made with the exposure. To quite a degree, you can, I once took a picture of a sunset, and I turned around, and there was a rabbit looking up at me, and of course I just snapped the picture of the rabbit, but of course I had the camera completely set up for the sunset. The JPEG had no rabbit in, but the RAW I could pull it up and see the rabbit. So it's even though he was probably about 7 or 8 stops underexposed. So he appeared black in the JPEG, but he was there in the RAW pictures. ISO sensitivity. You need to be sensible about sensitivity, because when you're working in low light, the temptation is to crank it up as far as it will go. And that doesn't really work. Depending on what your camera is, some are better and some are worse at this, and basically the bigger the sensor, the better they are at it. So I would say if you're lucky enough to have a full frame camera, then by all means use ISO 6400. But if you're using a micro four thirds like me, I don't really push it past 1600, 32 maybe on a good day. I've taken Auroras at 3200, they work. But compact cameras, they're no good past 400 because the sensor's too tiny. I work in the TV business, and one of the cameramen, in fact he's the chief cameraman there, came to me and he said, "Do you want to see my new camera? It sees in the dark." And I said, "Well, that'll be interesting." And I'm just in the backyard of BBC in Belfast, and he had this camera, Sony A7S II. It's got a maximum ISO setting of 409,600 on it. And I sort of thought, well, what's the point of that? And actually, I just grabbed hold of it and pointed it upwards, and in the middle of light polluted Belfast I could see all the stars in my viewfinder. It was quite extraordinary, and you know, that was a hand holdable thing, but that camera is renowned for it. It is the most sensitive camera. White balance you can set. Now it is probably about the one thing where automatic is all right, but now then I'm going to admit Mike Fallon. There we are. So I must be the host. But sometimes, if you happen to live in a sodium light polluted place, you will get a nicer colour to the background sky if you've set your white balance to tungsten. It's becoming much more difficult these days because it used to be just a few years ago that all light pollution was orange, but with LED lighting, a lot more light pollution is white. And the difficulty with that is it's actually even harder to get rid of. So there we go. And sometimes they're actually making them brighter as well, which is not so good. Now, so focusing. It's absolutely critical, but there is one factor here that helps us, and that's that as far as focus is concerned, really everything in space is the same distance. I know some things are, you know, only a few hundred miles, and some things are thousands of light years, but actually that makes no difference to focusing. Anywhere past a kilometre or so is infinity as far as focusing is concerned. And that does mean that what you can do is you can focus up on a bright object and then go and take a picture of a dim one, and it will be in focus still. Magnified live view is great there, and I say lock it and leave it. You can, if you really want to, you can often autofocus on bright stars or the moon, and then just switch it to manual and leave it there, because you'll have done it right. But through a telescope, you know, you don't have autofocus anyway, so you use magnified live view and manual for that. Attaching your telescope to a camera. Now, here's a picture of one I did earlier. That's my old Sony DSLR, connected to a Dobsonian 10-inch telescope there, and pointed at the moon up here. And what I've used there is what's called a T-mount. Now, most telescopes have this thread here, a T2 thread it's called, and you can buy an adapter from that to any camera. So this one shown here is EOS, so it's a Canon. And so once you've got the appropriate adapter for your camera, it's that simple. You just clip the two things together and you should be able to see them. Now, sometimes it gets a little bit difficult in that some telescopes, and I've got one which I had to modify, your imaging sensor is then too far away to actually get focus in it. And what I've had to do with one of my telescopes, it's a 5-inch Skywatcher reflector, is I've taken the mirror out and just put some additional nuts in to lift it a bit further up the tube, and then the mirror does focus onto the camera sensor, having done that. You can also use one of these. That's an eyepiece mount, in which this clips onto your lens mount of your camera, and it converts you to a 1.25-inch eyepiece tube. And the only trouble with those is that they're a bit insecure. because you've only really got one little screw usually to tighten up on there, and what you don't really want to be doing there is having your camera fall off expensively. And so what I tend to do, and you'll see what I've done here actually, I've just wrapped the camera strap around parts of the telescope so that if that did fall off, it wouldn't hit the ground. The other thing people used to do, and this is what I was saying about phones, it used to be very popular with compact cameras, digiscoping mounts, or astronomers have always called this afocal coupling, but digiscoping is actually a bird watching term more than anything. It's where you put your compact camera and it looks through the eyepiece of the telescope there, and you get little brackets that keeps it in place. Excuse me just a second. That's better. So that's how you connect up your various cameras to your mounting. The other thing now, you're going to find one thing that's very useful is taking a load of pictures. Instead of just one, take lots of pictures the same without moving anything else, and you can buy, if you haven't, camera hasn't got one built in, mine has intervalometers built in, you can buy one of these. This is a Canon, so it probably cost about £100. Mine's called a Young Chow, I think, or something like that. It's the same, only it costs £20. Made in the same factory in China, that's what that is. And you can do various things with that. You can, once you've got loads of pictures the same, you can stack them up to reduce noise. You can animate things to show movement. You can stitch things together to cover a wider area. Or you can make slideshows of things happening. And here's some examples of things that I've animated. Now I did this quite recently. You know that the skies in May during lockdown were fabulous actually here, and this is an hour's worth of multiple exposures just stacked up together with a free program called Star Stacks. You just feed loads of still pictures into that and it performs the magic on them to add them all up. And this is just me pointing the camera up towards the North Pole. That's the pole star there. And then all the others are just stars going around it. And I've even caught a meteor here. Just there. That's one of my frames did actually have a meteor in. So that was quite lucky. That's animated stuff. That's an animated moon set. So that's taking a photo of the moon setting, camera pointed in exactly the same direction, and just letting the moon drift across the field there while I'm taking pictures, in that case I think every 20 seconds or so, and I just take those pictures over a period of 5 or 10 minutes and stack them all up in Star Stack, and that's a nice moon set. Okay, that's similar, except that is the moon and that is Venus. And unfortunately there was a little tree in the way there, and a couple of little twigs of the tree got in the way of Venus there. But this is Venus and the moon setting next to each other, just a few degrees apart in the sky. Right, I'll just do a bit of explained stacking with deep sky images, and this is the Seven Sisters. 3 sorts of frames. Here you take 3 kinds of pictures, and these are your pictures. These are ordinary pictures. They're sort of 15-second, 20-second exposures, something like that. I'm on a mount here, and get about 20 if you can. This is a bit light polluted, you see. It's taken in my sky here in Larne. I've then taken the same pictures only with the lens cap on, and you say, well, why do you want to do that? Because what I'm getting then is pictures of my sensor noise, which I've bumped up here so that you can see it. I'll take 10 of those perhaps. And then there's another thing called flat frames, and flat frames are a bit of a strange thing. You do them with the same setup, but you do them the following day in sunlight with a white t-shirt over your lens or telescope. And what that does is that gives you a rendition of how hot in the middle your optics are. All lenses tend to be hot in the middle and darker in the corners, and you want to correct that, because when you process this to get more detail out of it, you want to do serious things with the amount of contrast in the image. And you therefore want the image to be evenly illuminated, and flat frames allow that correction to take place in Deep Sky Stacker. Now this is Deep Sky Stacker. This is that image fed into it. Total minute 3 minutes 45 seconds in 15 frames. So that is 15-second exposures. And this gives a very flat grey image, but it is pretty much noise free because all that noise in those 15 frames has averaged out. Signal adds up, noise averages out. That's how it works. But it's very flat and grey. So what I do next is I use this set of controls down here, which is a curves command, to increase the contrast in this part of the histogram here. So what I've done there is use that. I've increased the contrast greatly. And now you see some detail coming out. You see nebulosity there around Merope and Electra. And you can see that there are many, many more than 7 sisters. In fact, there's a couple of hundred there, all part of that same star cluster. So I've got a much better image out of that. It's a little bit noisy still, but if I'd taken more pictures, it would be less noisy. But that's a straightforward Deep Sky Stacker. It's quite a clever piece of software. You give it what it wants, and it gives you nice pictures at the end, and that's how I like it. It has aligned every frame of that, so that even if your tracking's not perfect, it sorts that out for you. Okay, here's just some general pictures I've taken. We'll sort of go through these, and I'll tell you what I've done. Here's just a great wide field picture of the sky. The moon is up the top here somewhere, but here's the 7 sisters here. And then I've got planets Venus and Jupiter and the great square of Pegasus there. You can just see the Andromeda Galaxy there because that's where it is. What I've done here is I've just gone up to the top of the hill from my house, and I've taken this picture. It's about 10 seconds or so, and I've waited for my moment for a nice man to drive his car past me. So I've just got these light trails here just to make it a bit more interesting. So that's that one. Here's a super zoom camera, a bridge camera. This is a Lumix FZ200, which has a 600mm equivalent lens on it, f2.8, and that's just pointed out at the moon. 80th of a second. It's cropped in a bit. It's through thin clouds, so you've got this sort of blue ring around the moon, and then this outer rust-coloured thing that you get, and that's called a lunar corona. This was the first astrophoto I ever took in New Zealand in 1997. I had never, although I've been into photography for about 20 years and astronomy for even longer, I'd never until this point actually put the two things together. And what's going on here, I was looking at the most amazing moonless sky in a place called Franz Josef Glacier in New Zealand. I thought, can I take a picture of this? And I've got my film camera with like 200 speed film in it. I've got a 51.7 lens, and so I just put it on a tripod, pointed it up, thought, well, let's try 15 and 30 seconds. This is 15. And it's the one that worked best by a long way. And what we've got here, we've got the Southern Cross upside down here. That's Alpha Centauri. That's Beta Centauri. I decided I have got Proxima Centauri there somewhere, about there. This is the Carina Nebula, because film is very good. Unlike digital sensors, film is quite good at deep reds, and that's a red nebula that's come out quite well there. So that's film, 1997. So that was the first time I ever did this. That's a bit later, 2002, but also still film. Total solar eclipse in Australia. Handheld. I could have done with a tripod, but actually I was there to see the eclipse, and the eclipse lasted 32 seconds. And so, but I did have a camera around my neck, so I picked it up. Okay, I'll try and get a picture. It's not perfect, but it's okay. And this is a very short duration total solar eclipse, and so there is light either side of it because the shadow of the moon on the Earth's atmosphere is not very wide. So that's Australia, 2002. This is more recently. This is the Andromeda Galaxy, and this is quite a lot of exposures. done with deep sky stacker, as we saw there, and an equatorial mount and a fairly long lens, 200mm lens, digital camera body. And that's the Andromeda Galaxy. If I'm critical of this, I would say I've left a little bit too much sort of blue background in it, which I could probably usefully tune out, but it's pretty good. You can see like the dust lanes and stuff. What you don't realise about the Andromeda Galaxy, apart from the fact that it's the furthest away thing you can see with the naked eye, you only ever see this bit, really, this fuzzy ball in the middle. But this here, the spiral galaxy, is 4 moons wide, so it's really quite big. If it was brighter, it would look fantastic in the sky, but it's not very bright. So that's the Andromeda Galaxy. That's the Seven Sisters again, another attempt at the Seven Sisters. I've picked up a fair bit of nebula around the stars there, but not quite as sharp as the other one. This is Orion Nebula. So you've got M42 and M43 here in Orion's sword, and up here you've got the Running Man. The Running Man is the dark nebula on top of the light nebula there, so that is called the Running Man. Yeah, so that's that. This is the Ring Nebula, Messier 57, sort of not very far from the star Vega, a bit down towards the horizon from Vega. That's an open cluster, Messier 35. Incidentally, Sinead, you were asking about M87 and what those numbers, right? All the M numbers, there are 110 of them. They were catalogued by a Frenchman, Charles Messier, in, I forget exactly what time this was, 17th century or something like that. But here's why he did it. And I would find this is a slightly strange story. He made a catalogue of these 110 objects because he wasn't interested in them. And if that sounds strange, he was looking for comets, which sort of, comets come and go. So he made a catalogue of those things that were always there that were not comets and therefore of no interest to him, so that he knew what he wasn't looking for. I know that sounds very strange, but that's the story of the Messier catalogue. That's Messier 35, and then there's another little cluster next to that. This one is Messier 51, which is the Whirlpool Galaxy, and this is very famous in Ireland because it was discovered through the Leviathan telescope at Burr in County Offaly. I assume you guys have, because you're not far away from it, you've probably mostly seen that. I've been there and I think it's a magnificent piece of machinery. It's easy to remember this. It's a 72-inch telescope, that is to say it has an aperture of 6 feet, and it was the largest telescope in the world for 72 years, until the one in Mount Wilson in California, which is 100-inch, took over in about 1911 or so. But that's still there, and I think they're doing some work on trying to make it vaguely operational again. That's a globular cluster, Messier 13, best globular cluster in the northern hemisphere sky. Unfortunately, the southern hemisphere has 2 better ones, one of which I have seen, which is one called 47 Tucani, which is like that, only bigger and brighter. And I looked at that through a 15-inch telescope, and the guy just said, "Come on, mate, have a look at this." And because it's full of stars, it's fantastic, and it really is impressive. But Messier 13 is the best one we've got, and that's not bad at all. In the constellation Hercules, quite easy to find. This was a weird thing that happened. This is the Andromeda Galaxy, and a comet came past it. And this isn't the greatest picture I've ever taken, but I sort of had to have my equatorial mount propped up against the side of my garden so that I could see over the roof of my neighbour's house to get this. You know, but it did come out quite well. This is a comet, Comet Pan-STARRS of 2013, passing the Andromeda Galaxy. North America Nebula. It is red because it is a star-forming region of hydrogen alpha light. It does bear this uncanny resemblance to North America. So you've got you've got the sort of eastern seaboard of the United States here, and then Florida and the Gulf of Mexico and Mexico itself there, and California and Canada up here. It really does look like the North America thing, but that's it. It is That's just next to the star Deneb, which when you look at the three stars of the summer triangle, Deneb is the top left one of those, and this is just about 2 degrees off to the left of that, North American Nebula. It's quite difficult to capture because it is this red colour that digital cameras aren't very good at. My Sony was reasonable at it, and I got this. And really I just processed it and processed it and processed it till I got more and more each time. But it was quite hard work. This is double cluster in Perseus. Very nice little cluster, sort of just beneath Cassiopeia, just beneath the W of Cassiopeia. They are actually 2 clusters together. They are in the same place. And there's this nice little thing here called the string of pearls that comes out from it. You see there, and there's also a nice red giant star in the middle there. This is a different thing entirely. This is a very, very thin crescent Venus in the daytime. And I would just say, Gerrit did his warm-up and said that something like this is happening only in the morning, around the 19th of June, where it will actually go behind the moon a bit. All of this sort of thing, you're pointing a telescope very, very close to the sun, and I would really say, unless you're really sure of what you're doing, don't be doing that. The way I did this was I actually put the sun behind my house so that I couldn't accidentally point the telescope at it, because you only do that once. But that's Venus. That's Venus also. This is one of those theoretically impossible photos, but I could do it anyway. This was Venus 5 hours before inferior conjunction. That is to say, when Venus comes between the Earth, between the Earth and the Sun. Except that on this occasion, because the solar system is not quite flat, Venus was actually about 7 degrees off the plane of the Earth's orbit. So I could actually get it before sunrise for just about 20 minutes or so. So I did manage to get that there. Something else entirely topical, noctilucent clouds, not really astronomy because it's not quite beyond the Earth's atmosphere. But these are the highest clouds in the atmosphere, and you can see them at this time of year, where the sun doesn't quite go that far below the horizon, and there is still some light in the sky, particularly where I live up here in the north. It just does not get dark. 1:24 would be my actual local midnight, accounting for British summertime and all that. But you get these wonderful clouds, waves and swirls and things, and they all move. So time lapses of these are good. I tend to go to Ballygally, which is where this is the Ballygally Bear, which you may have heard of or not. Okay, Aurora Borealis, same place, exactly the same location. That was an aurora that took place on St. Patrick's night. Oh, someone else wants to come in. Here we go. This was St. Patrick's night 2015, somewhere near the solar maximum, and we got a really good aurora that night. But what I've done with this one, I'll do a bit of management of expectations here, if you like. My camera, of course, can expose for 20 seconds, which is what you're looking at here. So you're looking at about 20 seconds, ISO, I think about 16 or 3200, something like that. It was quite misty, which is part of the reason it's not very sharp. But also, this is all moving, and over the course of 20 seconds, it moves quite a lot. My eye cannot do 20 seconds, or ISO 3200 for that matter. And so what I've done with this is I've reprocessed this to give a rendition of what I saw, and it's like that. Much fainter, much more desaturated, no red, teeny bit of green, completely different. But what I did see was that it was all in motion, and my still camera doesn't capture that either. So there we go, that's that. This is another aurora. This is early on in the solar cycle, up at Ballygally, with the plough in it this time. I've got there's the familiar outline of the plough. And that was 2011, so about 2022 we hope to get back to that sort of thing, and then better further on. We're at the very bottom of the solar cycle now. There's hardly anything happening on the sun at all. This was a combination of the aurora and star trails. There's 50 different pictures in that, all added up in star stacks. So you get, here's the pole star and all the stars going around that. Here's the plough actually up here. Those stars there are the plough. The sea looks nice and green as well. And that's actually an original version of it. The difference between these two pictures is oops, that one I've taken it with a fisheye, 7.5mm fisheye lens, but I've straightened it out afterwards so that the sea is actually flat. This is the original fisheye version where the sea is not flat, and I've got loads more in. That was such an all sky aurora that, you know, it really did go right above and more, covered the whole sky, and I had to use a fisheye to get it all in. That's that. Stacked up in star stacks, which is very good. Close up, this just illustrates a point. You can see from watching the stars go round, you can determine where the North Celestial Pole is, because it's in the middle of the wheel that they all form, right? So it's about there. Not quite where the pole star is there. If you get to really critical polar alignment, that difference becomes important. For most things, if you're not using very, you know, you're not doing hugely long exposures, and you're not doing, you know, huge telephoto or anything like that, then that difference doesn't really matter. But if you're ever wondering why your polar alignment isn't quite good enough, it'll be because you've gone for the pole star and not for the North Celestial Pole. They are just a little way apart. Here's another one. This is done with a webcam. The solar system is nearly flat, and sometimes that becomes a thing. And this is Saturn in 2007 emerging from behind the moon. And this is what I call one of those Father Ted things. You know, that you would look at this and sort of say, well, the moon is much bigger than Saturn. But actually it's the other way around. Saturn is much bigger than the moon. In fact, the body of Saturn there is 32 times the moon's diameter, but it's 4,000 times further away. So that's why Saturn looks quite tiny as it comes out from behind the moon. That's a webcam rendition of Saturn. Things to notice about this: Saturn wasn't anywhere near opposition. And how do I know that? Because this shadow here, when Saturn is at opposition, there is no shadow, because the Earth and the Sun and Saturn are all pretty much in a straight line, but we are off very much to one side at this point, so you do see that shadow, or that's the shadow of the body of Saturn on its rings there. The moon has colour. You can take a picture of the moon and step by step ramp up the colours a bit, and these are fairly genuine in that the blue colour, I'm told, is indicative of titanium, and the rust coloured thing is unsurprisingly indicative of iron. That's a total lunar eclipse, a sort of a time sequence thereof. This is the moon in the Earth's shadow. Now, the Earth's shadow is not a hard shadow, because the Earth has an atmosphere, and so light refracts through that atmosphere and turns the moon a deep red colour. And you can see here, this is the full moon. This is just going into the shadow, and then as it goes further into the shadow, you can increase the exposure and get that red coloration, and then it comes out the other side, and you come back to where you started from. And that whole process takes a couple of hours or more. So that's a total lunar eclipse. This is the sun, as always, saying don't do anything with the sun if you don't know exactly what you're doing. Ideally, the first time you do it should be with someone who knows what they're at, and they can check your work. But this was the sun a few years ago. You wouldn't see the sun like this now, because it's covered in sunspots. And actually, I mean, there is just one very, very tiny sunspot now, but nothing like this. I think this was about 2013, I think. This is the sun again, a few years ago. And this is shot through a very expensive hydrogen alpha telescope. that belongs to a friend of mine, and this is great. When you look at the sun in this light, hydrogen alpha, you see all these prominences around the outside, and then you see these here, which are filaments, which is the same thing except not on the edge. Now this here, this filament, if that was on the edge, it would be absolutely fantastic. You'd see it sort of stretch right out into space like that. But there it is there. Let's put it this way, I don't have a telescope myself that does this because I'd rather have a car, because the same money is about what we're looking at here. That is an expensive thing. Total solar eclipse. I went to Turkey for that one and slightly messed up my focus, but that's what a total solar eclipse looks like from the ground. I've seen 3 now and they're all been very different, but it was worth going to. And I think if everything gets back to normal by April 2024, there's one visible in Texas that I might try and find my way over to see. That's my favourite crater. Whoops. What happened there? Yeah, that's my favourite crater, which is Clavius. I like the eyes of Clavius here that you see when the light's shining on it just the right way. And Clavius, I use this in my sort of outreach a lot. I talk to people sort of locally around the north here, and I always use Clavius as my example crater because it is the same size as Northern Ireland. So that is to say, I'm in Larne just here, and you guys are sort of somewhere down here. And this is, if you took your car there, you could drive across it in about 2 hours. So that's about how big Clavius is. This is just a good indicator of scale. Now then, I'm coming to the end of really what I was going to talk about, but I'll show you a few things I've been doing recently. I've taken to using my 4K video camera, and this is it. It's a Panasonic. And one of the things it's got about it, it's a very good video camera. It's a good still camera, but it's an even better video camera. And it shoots in 4K video, which is 4 times the resolution of your 1080p high def. So every frame in it is 8 million pixels. So it's nearly like having a still camera that does video. 30 frames a second, and it's good for detailed images, and it's good at capturing fast-moving objects. And I'll show you examples of both. When you look at something like the moon, what happens is all that light is coming through the atmosphere and it shimmers, it wobbles around a lot. And what you can do by capturing lots and lots of pictures is you can feed that into software which will decide which are the sharpest images, i.e. those where the light has come straight through the atmosphere without being wobbled around. And you can pick those out and then you can stack them up and you get very sharp pictures of the moon, which I'll show you in a bit. But also now capturing fast moving objects. I'll show you some things I've done here fairly recently. Here we are now. This is recent. This is the International Space Station here, passing in front of the moon. Now I did this in lockdown, so if I'd gone a bit further up the road through not being in lockdown, I could have got that more central. Because this actually, where this happens, is only a couple of miles wide. But this is the space station here going in front of the moon during daytime, hence the blue sky. And what you get from this, actually, the space station is more reflective than the moon, so you still see the space station in front of the moon. There, that's one of those. That's another one that I did at night. Now I did that 2 years ago when I wasn't in lockdown. And so I was able to go up the road about 15 miles up the coast to Carnlough, where I did this, and this has gone right across the middle. Yeah, this was at night. This is approximately midnight I did this. Just pitched up, threw my telescope up, put the camera on the back. And you're looking at about, well, each one is a 30th of a second. So you're looking at about 2 seconds of video there. And one of the things that you do need, that makes all this possible, you go to a website called transit-finder.com and tell it where you are, and it will tell you when this is going to happen. And it tells you very accurately when this is going to happen, and you can rely on the fact that in this day and age your phone is an accurate enough clock that you can be running your camera at the right time and get this. Of all the problems I've had getting these, the time being wrong isn't one of them. I've had trouble with the wind and all sorts of other things, but and what I'm doing here, very short video exposures, so about 1/1600th of a second and 30 frames a second. So each of those is 30 frames apart, and because the International Space Station travels at 5 miles a second, you can reckon that every 6 dots is what is it now? Every 5 miles a second. So every 6 dots is a mile that the space station has travelled there. Is how that works. This is a similar one, except that that's the International Space Station going in front of the Sun. Now the same caveat, follows there. Please do not point anything at the Sun if you're not absolutely certain what you're doing. I've used a Barda film solar filter there, so I've got a good exposure. Again, nice fast exposures to freeze the motion of that thing, because that is travelling 27,000 kilometres per hour. So it doesn't take long. You're looking at about 2 seconds worth of video for that whole thing there. 1.7 seconds, I've decided. And so that's that. This is some moon work that I've done using the same technique, 4K video. And that's the crater Copernicus and Kepler down there. Lots and lots of detail comes out of that. Again, that's picking the best frames from video and then selecting them for quality and stacking them up. I use Auto Stack It usually, but there is another one called Registax that some people use. I just find Auto Stack It a bit easier. There's a thing called PIPP, the Planetary Imaging Preprocessor, and it's extremely hard work, and I haven't really got a complete grip on it myself. But what that does is that crops images, stabilizes your image for you. So if there's a bit of movement going on, it doesn't matter. And picks out the best ones, and it's some sort of magic, and it's so configurable that there's so many options that I kind of fiddle around with it till I'm happy with it, but I don't really know what I'm doing yet with it. There we go. There's another one. This is so here. This is the Sea of Serenity. This is the Sea of Tranquility. And this is the Sea of Crises up here, the Mare Crisium. And approximately here, right here where my mouse pointer is, that's where Apollo 11 landed. Just where my mouse pointer is, just about there somewhere. And no telescope from Earth can actually see the lander, but you can see it from telescopes that are in orbit around the moon now. So that's it. So there you go. That's it. That's all I have to say. Do you want to unmute and ask me any questions you might have?